Okay, so today's lecture is about covalent bonding part 6, and the title of the lecture is The Start of Something Sweet. So it's true that humans derive the majority, that means they gain or they get bulk most of their caloric, that's a C, caloric intake, from carbohydrates, both simple and complex. Well, what are simple and complex carbohydrates? Well, today we're going to talk about simple sugars or simple carbohydrates. And simple sugars include both monosaccharides, for example, glucose, fructose, and galactose. We're going to draw these two today. And disaccharides, which includes sucrose, maltose, and lactose. Okay? And we'll draw this guy today. And in order to understand what a disaccharide is, we first have to understand what a monosaccharide is. So monosaccharides come from this, consist of one, okay, mono meaning one, saccharide meaning sugar, okay? And sugars are chemicals that exist in this ring structure or ring form, and those in fact are carbohydrate monomers, and we'll get more into what that means later. But for now, you can understand that sugars, large sugars like starches that we eat when we get potatoes or bread, right? Or cellulose, which makes up actually most of the wood, right? If you have like a piece of wood, most of that wood is actually cellulose. Okay, that's an indigestible by humans sugar. If you're a termite, you can eat that. Those larger sugars are made up of repeating units of smaller sugars, and so these individual sugar rings repeat over and over and over, and we'll start to understand how that works today. Okay, but those individual monosaccharides are in fact carbohydrate monomers in larger sugars, which are called polysaccharides. Which we will discuss another time. So we get most of our caloric intake from sugars, right, of some sort, and monosaccharides are the simplest of them. Okay, well here are two monosaccharides we absolutely need to know. So the first one is called glucose. Okay, glucose. And glucose looks like this. Okay, so this is glucose, and this is the skeletal structure for glucose. And so, wow. So what in the world is this thing, right? So the first thing we need to understand, actually, is that glucose is blood sugar. So we would all be dead right now if we didn't have enough of this in our blood, okay? Not like any of it, right? If you just don't have enough of it, you've got to have a certain level of it in your blood in order to live. Okay? If you don't have enough, the first thing that happens is you slip into a coma. The second thing that happens, if that never gets recovered, or if your body is just not recoverable from that state, is that you die. Okay? So glucose is extraordinarily important to human health. It is, again, blood sugar. But it also comes from other places, and we'll find it elsewhere, all over the place actually, and we'll discuss that too. But for now, we understand that this is blood sugar, and we should also be able to figure out what its chemical formula is. But I'll give you a little bit of help because it's been, we've had the weekend, and so we need to be refreshing ourselves on skeletal structures. Okay, so this consists of three types of atoms: carbon, hydrogen, and oxygen. First order of business, let's count all the carbons. Okay, so with me, corners mean which element? Corners mean carbon. Everybody say it. Corners mean carbon. Good. So let's look, right? We see a corner here, we see a corner there, and there, and there, and there, and there. They all correspond to carbons. Let's count how many carbons we have. Ready, set, go. 1, 2, 3, 4, 5, 6. Okay, so we have 6 carbons. So the molecular formula for this guy is going to start out C6, okay? C6. And it's actually going to end with the number of oxygens that it has, right? So the beautiful thing about skeletal structures is that every atom that's not carbon gets drawn, and every atom bonded to that atom, no matter what it might be, also gets drawn. So the O gets drawn, and even though we don't draw hydrogens that are bonded to carbon, we draw them when they're bonded to anything that's not carbon. So how many oxygens do we have? Ready, set, go. 1,
2, 3, 4, 5,
6. Okay, 6 oxygens. 6 oxygens. All right. Now the hydrogens. There's one hydrogen here. And here's a corner where there's a carbon. Now carbon makes how many bonds? 4. Okay, everybody focus. 4 bonds. But if 2 of those bonds are taken up by an oxygen and another carbon, how many bonds does this carbon have left to make to hydrogens? 2. Okay, H1, 2, 3. So at this point we've got 3 H's. How many H's right here? 2. Okay, now this carbon here makes how many bonds to other carbons or other things that are not hydrogen, right? It's got 4 to make total. It makes 1 to an oxygen, another to a carbon, and this one's to another what? This bond is from one carbon to, what's at the corner?
Carbon.
Carbon. So this bond right here is from one carbon to another carbon. That's a carbon-carbon bond. Good. So this carbon makes how many bonds that are drawn?
3.
1, 2, 3. Okay, 3, right? So that means it's got how many left over for hydrogen?
1.
1. So CH1 right here. Okay, CH1. So let's count from the beginning. How many hydrogens? 1, 2, 3, 4. Okay, now we go over here. This carbon is just like this carbon. It's making 3 bonds that are drawn. Okay, 1 to an oxygen, 2 to other carbons. So how many bonds does this guy have left? 4 minus 3 is
1.
for hydrogen. Okay, let's count from the top. 1, 2, 3, 4, 5 hydrogens. Now this O here has a hydrogen, so we can count from 5 to 6, right? We got a bond. This carbon is just like these other 2 carbons, so it makes how many carbon-hydrogen bonds? 1. Okay, 7. Then we've got another hydrogen here, that's 8. This carbon is like the others, okay, so it has 1 hydrogen, so now we've got 9, 10, 11, 12. Okay, that's right. Let's count from the top, but that's right. Ready, set, go. 1,
2, 3, 4,
5,
6, 7,
8,
9,
10,
11.
12. H12. Okay. And now for something that's actually quite beautiful. So, there are these moments in science when math and vocabulary and what we're learning just add up to something we wouldn't expect. And I guarantee you, the initial chemists who studied this did not expect this. So, how many of us heard about carbohydrates last year in Mr. Newman's class? Right? We heard about carbohydrates. And how many of us have heard about carbohydrates on TV, like low-carb diet or so on and so forth, right? Or like you think about them maybe when you go to Costco or when you're out grocery shopping or whatever, right? So this carbohydrate idea, this word, is not foreign to us. But what does it mean? And where does it come from? And why would Dr. J think that's beautiful or cool? So this is a cool moment right now because it's an intersection of chemistry and math. We know this word carbohydrate, right? So I'll write it on the board. I'm going to erase it in just a second, but find a spot in your notes for it. Okay, so carbohydrate. There we go. Okay, so what's the greatest common factor of 6, 12, and 6? Think math, right? What's the greatest common factor of 6, 12, and 6? 6. Okay, very nice, Anthony. So, what's 6 divided by 6?
1.
Okay, I'm just going to put a C there. What's 12 divided by 6?
2.
I'm going to put H2 there. What's 6 divided by 6 again?
1.
1. I'm going to put O there. Now watch. We've thought about this, we've heard this word, practically our whole lives, right? And it turns out that these chemicals are called carbohydrates because they have this really interesting atomic ratio, okay? We call this an empirical formula. And that formula, or that ratio, is 1 carbon to 2 hydrogens and 1 oxygen, right? So carbon And then H2O is the formula for water, right? Carbohydrate, okay? That's where that comes from. That's why that's cool. That's why that's interesting. Just on its own, right? The chemists the pioneering chemists who studied this stuff ended up coming up with, or realizing that all carbohydrates had roughly this same formula, okay? This holds for all simple sugars. It gets a little more complex when we're thinking about disaccharides and polysaccharides. But roughly that ratio holds for all of sugars, and that's where it comes from. 1 carbon, 2 hydrogens, 1 oxygen. Carbohydrate. Okay. So I'm going to go ahead and erase that guy. Well, I'll erase him in a second. But before I do that, I'm going to give you one more thing to think about, right? And glucose is sugar that's in your blood. We've got another guy, and this guy's called fructose. And fructose is a sugar, and I always have to, I don't draw him as much as I draw glucose, so I got to make sure I'm getting him right. But fructose is a sugar that's in your fruit, okay? So fructose is fruit sugar, and it's in other places too. Okay, it's got an OH there, it's got OH there, it's got a corner there leading to another OH, then it's got OH there, then it's got OH there, and then that's it. So this guy is fruit sugar. What I want you to do with your group, okay, in a little bit, is figure out his formula. But I'm going to show you one last thing. So I'm going to erase this now. I'm going to show you one last thing before we start getting this guy's formula and then eventually building. And this thing is really, really cool. So, it turns out that glucose and fructose, fruit sugar, blood sugar, actually show up in a couple other places. So when you sweeten your tea, you can sweeten your tea or your coffee with sugar, but you could also use something else. Not a crystalline substance, but a liquid. A thick liquid. What's that thick liquid that we squeeze out of the bear into our tea sometimes?
Honey.
Honey, right? Thank you, Larry. Okay. So it turns out that you've been well acquainted your whole life with glucose and fructose because they are the primary sugars in honey. Okay? When you eat honey, you're eating a mixture of a lot of glucose and a lot of fructose with some water, right? There's water in there to give it that nice thick, like liquidy, fluid characteristic, okay? So that's why it flows. But a lot of dissolved glucose and fructose in that water. Okay, that's what you're consuming. Those are the sugar components you're consuming. But here's what's crazy. Here's what's really crazy. These two don't just exist in isolation from each other. Actually, they're found bonded together chemically. So this is what that looks like. And then let's go. So, we recognize this little guy on the left as a glucose monomer. We recognize this guy on the right as a fructose monomer. But this is not, okay, this is not a monosaccharide. This is glucose and fructose bonded together. and a disaccharide, those are both C's there. This is called a disaccharide because it's got two sugar rings, okay? Two carbohydrate monomers, okay? Disaccharide, there are two of them, okay? Two sugars. And it turns out when glucose and fructose get together like this chemically, they form none other than table sugar, otherwise known as sucrose. Okay? That's what this guy is. Disaccharide table sugar. So today we're going to do a couple of things. One, we're going to figure out the formula of this guy. Two, we're going to try to actually build these two molecules, which is not as easy as it looks. Okay? We also have a lot of questions in our mind, right? So we've been thinking about our essential questions. How are molecular compounds structured? Well, this is how sugars are structured, okay? Some really important ones. Glucose, fructose monomers, and then the glucose-fructose dimer